I'll go through the history of the dish, briefly how radio telescopes work, examples of famous ones, what they hear, a bit about us being stars, which is Niall's baby, but it's absolutely true. Then I'll go through the 3 phases of the big dish with Niall and a bit about the future. So just to start off, this is the picture from the gate in Elfordstown. You can see it was built in 1984. The big dish in the middle is a 32-metre C-band antenna. The one on the left is a secondary C-band antenna. And on the right-hand side you have a KU to the far right and a KA, which is a brand new dish just gone in beside it there. The background is this place was built as a communications post between Europe and America. The reason it was built was in the 1980s, if you wanted to make a telephone call to America, you used to have to send your call from here to your exchange across to the UK, and it was beamed from the UK, from Goonhilly, over to America. Now, the European telephone companies weren't happy because British Telecom were charging too much, so they got together and they set up a company called Eutelsat, the European Telephone Satellite Company, and this was tasked to build another another C-band antenna to send the signals to America, and that's where Elfordstown came in. National Space Centre, which is our company, we started off in January 2010, and the reason we're here is to promote both commercial broadcasting contracts and communications to satellites, but also space-related research in satellite and space research, working with the European Space Agency, the research establishments, and the blue-chip European satellite owners to deliver on this. This is a rough business plan, and it's sketched on the wall, but it's the simplest you can see to show what we want to do over the 10 years. We already have this dish in, a brand new one. This is the big C-band, this is the small C-band, this is the KU, and we're going to have 5 KA band dishes across the front over the next 5 to 6 years. 2 more reference dishes. We'll have an Earth observation post down here for taking down environmental feeds from various satellites. We're going to put in a building on the back for research and development with universities and colleges and research. And we're going to move sales and marketing up here out of the main building. So this whole building down here on the bottom is purely going to be for controlling and managing and monitoring space research and satellites. This then shows you the aerial photograph of the site today. Well, that was actually 2 years ago because it doesn't have the new dish here. But again, back to the drawing I had a moment ago, you've got the big dish on the roof of the big building. The main building is underneath this dish and around here. This is where we have 4 430 kV. They're huge generators. The generators in this building could run the whole of Middleton. So there's a phenomenal amount of redundancy and ability to stay going if there's a power cut. This is the secondary C-band antenna. And across the front here is we're going to put the other antenna, and here, and the research building in the back. Now, just to give you an idea of what these were for, this dish was originally the one for beaming to America. This was a backup. This one here used beam stuff to Cyprus. These all are decommissioned at the moment, and one of the jobs we're doing is to recommission them and get them all back working again. This is a photograph from the top of the site, and you can see the dish is better from here. KU, KA, brand new one, C-band, and the C-band on the bottom. This is the KU here. I'm showing you this in detail because this contract went live. This actually started broadcasting Tuesday this week. It's a huge deal because the contract that we're after setting up for here, we're one of 8 gateways around Europe. They've launched a new satellite called the KSat. This is one of the 8 dishes around Europe. There's ourselves, Helsinki, Bonn, Cyprus, Sardinia, Turin, Arganda, and Rambouillet in France. That's one as a backup. So they're the sites that are going to be beaming all the internet traffic up to the satellite and across the whole of Europe. I'll show you the spot beams in a minute. This is what the satellite looks like, and this was launched January this year. It's beaming over the whole of Europe down here, as you can see on the bottom.
8.
This is
7,
a video of the launch
6,
itself that happened
5,
in January.
4, 3, 2, 1. And we have main engine start off, and we have liftoff of an ILS Proton rocket from the Baikonur Cosmodrome in Kazakhstan with the KA-SAT satellite on board. Let's watch.
They were very nervous when this was being launched.
20 seconds.
And the reason they were being so nervous is because there's been many failures on launch over the last 5 years.
A roll maneuver. and soon experience maximum dynamic pressure, or max Q. Max Q is the maximum aerodynamic load on the vehicle, and it corresponds to about Mach 1.5, and occurs 1 minute and 2 seconds after liftoff.
Now that satellite is a geosynchronous satellite, and that is sent up to about 33,000 kilometers above the equator. It sits there and it beams down across the whole of Europe. The spot beams, and these are the beams that send information down, are 80 spot beams across Europe, covering right down as far as Russia, up across Norway, Sweden, UK and Ireland, right down to North Africa and around the Mediterranean. One of the big things about this new system is that for delivering television, it means you have lots of individual beams. The current technologies beam across the whole of Europe. The problem with that is, you know, do any of you have Sky? How many people here have Sky boxes? Okay, you know how you couldn't get RT in your Sky box? The reason you couldn't get RT is because they pay a very small fee to the Americans for licensing their programs. So they're not allowed beam across the whole of Europe. Sky pay much more, so they're allowed beam a little bit more. This technology means that you can take a television channel and you can beam just to Ireland. And I'll give you a zoom, and it's a bad graphic, but it shows you why. The spot beam for Ireland, which comes from Madrid via this system, beams just over Ireland. And there's 4 beams over the UK. So they can beam and not have any of it spill into the UK or to France or anywhere else, which means they can pay a very low fee for any of the television, Glee or Friends or whatever people like to watch. The big dish, now talking about the big dish, our dish is, again, it was built originally for telephone traffic. When you read the stories, it was built so it could handle as many as 300 phone calls at once. Now, nowadays they're thinking, oh my God, that's insane. But they were thinking there might be as many as 300 calls to America, which is quite staggering. But it's now being recommissioned, and we're trying to use it for the Deep Space Telescope. The opportunity with CIT has been a fantastic opportunity, because when we looked at the dish, this dish to replace would cost 10 million euro today. So it's a major piece of infrastructure for the country. And because it would cost so much to replace, it would be an awful shame to cut it down. And 3-4 years ago, Aircom were looking at removing it because it would be dangerous to leave it up there. And they were looking at cutting it up and selling it for scrap. Now obviously it's been a major deal getting this back into use for research. And Niall, who's down the back there, Niall has been fantastic in getting it working for very little. And I'll go through that in a minute, exactly how that works. But it means that we're going to have access to this for students and for education and everything else for very, very, very little money. This is a picture underneath the main dish. It's dirty, needs a good clean, but other than that, it's in good nick. Some of the wiring needs to be replaced around here, and there's bits of tin along here that are a bit tatty. It has been left run for about 2 or 3 years, but up until 2 or 3 years ago, it was kept in very, very good nick by Aircom, to be fair. This is a side photograph. This is an older picture from the front, but you can see the size of the front. This is just nearly 100 feet across, so it's a very, very large dish. Again, nice picture underneath, and this is a picture from the field. This is taken about 2 or 3 weeks ago. We've already cleaned off some of the frame and done some work on the inside, and slowly, bit by bit, we'll get it back in operation. Now, this is a brief run through how the telescope works, famous radio telescopes, and what they see in the Basically, we have distant radio source, all kinds of radio waves coming through. They're hitting this building, they're hitting the water outside, they're currently hitting our dish in Middleton. They have been since it went up. The only difference is we don't have anything at the moment listening to what it's saying and what it's receiving. And the way it works is that the radio source hits the dish, it's focused by the dish into the middle, and then it's bounced back down into the feed horn. Now normally this would take it into amplifiers and receivers, and it would concentrate it, and you would have recording equipment on the other side of it. In the initial stage, we're going to get this working quite quickly by putting a receiver just here. And this is why we're able to do it so cheap. This is an example of the Arecibo one. Now, I don't know if any of you see James Bond, where Pierce Brosnan goes running around this and big fight in the middle of it. This is it 100 meters? I think it's the biggest dish in the world, but it's a stationary dish. So as the world spins, this scans the skyline. We're going to use the dish in the same way in phase 1. So this is a very good example. The second dish that we have is Apple Valley in California. And this is the most similar to our own because this is 34 meters across, ours is 32. This is used for research, for students, for all the kind of things we want to get the dish here working for. And this is a key component of this. We want to get young people involved, we want to get them excited about it, we want to get them to see what's in space, to actively get involved. A picture of the universe with gamma rays, a picture in infrared, and these are just examples of the pictures that are coming out of space. And the next one we have a little video clip showing you some of them in various different forms. The Andromeda Galaxy is the one we'll be looking at. Example of the various different forms of light or radio wave that's being received, and it gives you a feeling for how important it is to have all these different sources. So when we're doing research here, we'll be tying in with various other research institutes, and we'll be putting that all together to give a much more complete picture. The beginning of the universe. Now this is just some stuff that's very interesting and tied in around why we're interested in this area. Obviously the Big Bang, start of time. Starts here 13.7 billion years ago, and the universe has been expanding and growing since then. When we look at these and we start looking at the pictures, this is another one of the expanding universe. The thing that really gives us an idea on this is, if you can imagine Lucy, our most ancient ancestor, or one of the most ancient ancestors, was about 4.5 billion years ago. Sorry, 4.5 million years ago, which is here. Okay, now the light that we saw a minute ago from Andromeda, that light left Andromeda when she was running around Africa. And it's taken that long for it to get here, which is like you're looking back in time when you're looking into space. And that's the exciting thing. The further we look, the further back in time we're seeing. And that's one of the really exciting things about the research here, is we're able to genuinely see back as to what was happening at the beginning of time, the beginning of the universe. We can see the run through. The more further back we go, the further back we're seeing. Crab Nebula. This is after a star's exploded. Another one with the remnants of a former star. The next one we have is one forming into a star. So you can see here huge dust clouds slowly getting sucked in together to turn into new stars. Like the thing for me that's amazing here, especially with a picture like this, is just you look around us. There's millions of stars. Just this little piece of space, there is millions of stars. It's astonishing. They're just so beautiful, the pictures are, and it's such an amazing area to be involved in. We want to get young people interested, get them kind of let them see what they can get into on the other side, rather than just sit in boring class and listen to formula. You know, this is the exciting side of it. It's staggering. This one I found hilarious. This one, are any of you familiar with this? Does it look anywhere familiar at all for you? Close. The Firefox logo. Outside of Firefox, and this is where they got the idea from. And this is mad stuff. You see this, and I've seen this frequently in photographs. We actually put a photograph of this up because we thought it looked gorgeous on the wall in the office. We have some of these pictures up. And it was only searching through for images for tonight, I came across this one with them together, and I was thinking, you know, I knew I'd seen it before. And this, our nearest star, the sun. Now this to me is an amazing photograph, because if you look at this eruption out of the sun, it is so huge, it is absolutely massive. If the Earth was directly in line with that, we would have serious weather problems, because that is such a huge emission. And these happen quite regularly. We're lucky that we don't have more problems with emissions from the sun. My favourite of all the pictures is this, and I've seen this before as a picture of Inside Heaven. And this, it really is spectacular. But this I adore, and this is where it kind of leads into and shows you where it is, the Carina Nebula. I just put that up because I think that's one of the most beautiful of all the ones I've seen. I think that is absolutely amazing. So the big dish now, Niall, I'd like to ask you up to come and give a few words about the plans for the dish, because Niall's actually the scientist.
Well, thank you very much, Rory. Before we go on to the plans for the big dish per se, this is a bit of a first here tonight. Usually we have either a really enthusiastic amateur, or a really enthusiastic professional, or somebody who has a background in astronomy. Technically, Rory doesn't. He's a businessman. And I think there's a perfect example here of somebody who's got an interest in astronomy. We shared a very long breakfast actually in Dublin recently, talking just about the universe as just an interesting place to be in. But what I think is really fascinating about this story, as it is at the moment, is we have somebody whose interest primarily from a business perspective is moving television signals around Europe, but they see immediately the opportunity to excite people, just like yourself, whose central remit in life is not to do radio astronomy, but nevertheless they understand that having this enormous dish is just really exciting. And one of the first things I would say on that is, if you go down there and you just stand underneath it, and you've shown some fantastic pictures of it, it's just an astonishing piece of engineering. If you never ever did any astronomy with it, it's just amazing. It's so huge. So as Rory says, I want to say in case I forgot, because I just think this is fantastic, and I think it's an enormous credit to Rory and the team down at the National Space Centre, they could have easily actually looked to sell stuff for scrap or something like that and made a few bob out of it. But they see a whole other thing that they can do with this radio telescope. So we don't often hear that enough, and we're in the midst of a time which isn't maybe the best in our history in terms of finances and so on. Lots of other things are really good in our society, but that's probably not the best one. And yet we can still look to the future. So this is a really good example of that. And that's a bit of a monologue, but I feel very strongly about it nevertheless. This is a case of putting your money where your mouth is. So Rory mentioned already how these things work. And the great thing is, and he already mentioned it, the Middleton dish has been receiving signals for years. It's just that when the signal bounces off this retroreflector here, or subreflector, it comes to a focus here. And in your camera that you would have on your mobile phone, there will be some sort of optical device to make a picture. Well, there's nothing there at the moment that works. So the first thing that we're going to do is put something there so that we can actually detect those signals. And remember Rory said about Lucy, that our great ancestor, one of the apes, we know we're sort of derived from that line of evolution. She was wandering the planet 2.5 million years ago, and that light from Andromeda started out 2.5 million years ago, as Rory pointed out. But just think, for the last 2.5 million years, it's been working its way towards us. It's been passing planets, it's been going through dust clouds, it's been skirting stars. Who knows what other amazing things those radio waves have seen. And then they come down to Middleton, they hit this reflector here, they've travelled for 2 million years, in a bazillionth of a second, they go down there, back up here, and much to their disappointment, nothing. So it almost seems like it's unfair on those waves to travel halfway or a large way across the universe with an amazing story to tell, because we don't bother to put something there to detect them. So in a sense, that's what we're doing now. We're putting something here to detect them. Rory mentioned this is roughly 10 million euros worth of equipment if you were to rebuild it. We're going to put something here for roughly 10,000 euro to bring the whole thing back to life. But in phase 1, the dish will be like Arecibo. It will simply point up at the sky, and we'll be relying on the sky moving, well actually it's the Earth moving really, to scan the sky over the top of this. And one of the things that we can do in phase 1 is to look at some of these wonderful gas clouds, dust clouds, gas for this cloud, hydrogen in particular, that's everywhere in space. And that's really very exciting, because our plan is to connect that so that you'll be able to look at what the telescope is seeing on the web. But there's an interesting element here. One of the first groups of people, because Rory is got an interest in science, but is also a very good businessman. I'm not a good businessman, I have a very good interest in science, or whatever way you want to put that. But actually, a couple of people in the art world have come to us and said, hold on a minute, if we're receiving radiation from space, there's loads of interesting things we'd like to do with that, to interpret that data, that information flow. And what this tells us is this particular dish can also be used by the artistic community. And in fact, when we eventually switch it on, we're going to do some fun things. I won't tell you what they are just in a minute. I'll leave that hanging, because we have some interesting plans for when we're going to switch it on, but we won't come back to that tonight, because that would be a bit of a surprise. But once the signal gets to here, then we'll have now detected it, and then we can then bring it to wherever we want to. And Rory mentioned about receivers, recorders, and so on. One thing that's interesting is that the original receiver, amplifier, and all of this fills a room 3 or 4 times the size of this room.
It's actually the underneath the big dish. You've seen the pictures of the circular building. That entire building is full of equipment, of radio receivers, amplifiers, waveguides, all the control systems. Actually no, the control units for the dish were in the second room. It was purely just the radio equipment that was in the big dish underneath.
And we're going to collapse all of that onto a PC. And that's as much a statement about 1980s technology and 2011 technology. And in fact, that PC now will spend most of the time doing nothing. it'll be kind of sitting there thinking, well, this is boring, there's not a lot going on here. Because PCs are so powerful, and the rate at which information comes to you, even in a dish this size, is relatively modest. The rate at which the data comes to you is relatively modest. Incidentally, in case you're wondering, why do we need such a big dish? I mean, Rory showed you smaller dishes and so on. Well, if you want to see faint things, and I don't know if you noticed this, even in sports photography, I don't know, for the younger or the older amongst you, you'll often see guys sitting on the sidelines in a football match, and they have this huge lens and this little camera, and they have it on a tripod and so on. And the reason they have the huge lens is actually they need to capture light. So they can take a very quick photograph so that you can kind of see the guy heading the ball or whatever it might be, and they capture it sharp. So if you want to if you want to do something quickly, or you want to gather a lot of light, you need a big lens. Well, we don't really want to do anything quickly, but we want to look at things that Rory said that are very far away. So they will be faint. So we just need a very big dish. So this is really fantastic to get this. Once we've got that signal, we can start to do interesting things with it. But then I suppose the next phase will be to have the dish moving. Now, we know the dish moves, we know the dish is capable of moving, but there's a bit of a job of work to do to make sure that we can do that on a regular basis, so that we can now do something which we won't be able to do in the beginning, namely point at an object and track it. So if we want to look at, for example, some of these of the most exotic objects in the universe, the quasars. Quasars are very far away, so they're quite faint. We want to look at them. We need a big dish. Check, we got the big dish. If we want then to see if they're doing anything interesting, if they're getting brighter or fainter or whatever, then we need to follow them. At the moment, when we switch this on, we won't have that. But that'll be our ultimate goal, to bring that. And as Rory said, then of course, once you have this data, you invite more and more people to collaborate with you, and you try to expand the work so that it can still be artists, but it can be kids in school, it can be interested amateurs, it can be other professionals, whatever it might be. And the other great thing about a radio, which is really nice, is it works 24 hours a day, 7 days a week, 365 days a year. So if you're in a school, for example, and your school is using this dish at 3 o'clock on Friday, no, it's going to be open at 3 o'clock on Friday, 12 o'clock on Friday, it doesn't matter if it's raining in Middleton, it doesn't matter if it's cloudy in Middleton, it doesn't matter if it's windy in Middleton. The radio waves don't notice any of that. And that's a big advantage, because then you know if you log into this system that you'll be able to see something with it. With an optical telescope, like we have here in the castle, if it's cloudy, well, it's just cloudy and that's it, and it's unfortunate. But with a radio telescope, cloud doesn't matter. So that's really handy as well, 24/7, 365 days a year. So the possibilities can go on one step further. If I might just finish with this. This is a single dish, it's on its own. But you can actually, if you have the money, and at the moment we're really talking about value for money. Let's remember what we just said here. So when you go home tonight and you're thinking recession, big dish Middleton, they must be spending a lot of money, what a waste of taxpayers and all that. Remember, we're talking about less than €10,000 to bring something that's 10 million back to life. I think that's pretty good value for money. I really do. I think if we could get that sort of leverage off everything we did in the country, we'd have our bank balances clear up very quickly. But what you can do is you can ultimately put more expensive instruments on the end of this. It's a bit like you can put the Rolls Royce on the end of that. At the moment we're putting a very nice Passat. So eventually we'll get something that's maybe a little more higher end. And the only reason to do that, by the way, is you get a slightly cleaner signal. And that's why you would do that. But you know, you get most of the way with the Passat. If you want the fancy bits, you go for the Rolls Royce. So we'll get most of the way with relatively simple equipment. But then we can link this telescope to other ones around Europe, and even the one you showed in the States, like Arecibo or this the Goldstone one that you showed. We can link to all of those in the future. Now that might be a few years down the line. But what we know is within about 6 weeks, we will have a signal. And just think about this, actually, and this is the last comment I'm going to make. Just think of right now, as we're sitting here, there is some radio waves that's coming towards the Earth. They're out there in space, they might be 6 weeks away, so they're way out beyond the solar system. But right now, they have no idea that they're going to be the first radio waves to come through the Earth's atmosphere, bounce off this, hit here, and not be disappointed. They're on their way right now.
So we just give you, this is an example of some similar dishes moving, and this is, as Niall was saying, this is the plan, to get all the motors cleared up, to redo the wiring, to clear down the bearings and make sure it's 100% before we move it. The reason we haven't moved it is we don't want to cause damage to the dish. And we want to be very, very careful because it is such an amazing piece of equipment. We want to make sure we get it back online and there is no problems. So we're being very careful. But you can see this is one in Germany, and this is the way the one in Cork can move. It's got a similar gearing system. It's smaller than this one, but it will work the same way. So that's the example of what we're at. The reason why and the road to the future is to try and expand minds, get people involved and interested, to tie in with the education establishment and encourage students and researchers to get involved in industry and create an industry here in the space sector. European Space Agency want us to do it. There's good money there, there's a lot of jobs there. It's an area that we have a lot of expertise in already. Many of the people we're dealing with across Europe are Irish. There's senior people right across the industry that are Irish. And it's to just try and get them to bring connections and jobs back in here and try and get more work for us all in the sector. So that's about it. Questions and answers. If you have any queries or questions about it. Yep.
So, let's get this straight, because I'm going to be confused. So he starts off on a commercial basis to receive signals from satellites, and is the stargazing a kind of spin-off?
No. You see, we've taken over the facility and the equipment is there.
Right.
And we've a choice. Either we get in the Loftuses and knock it down and sell it for scrap,
Right.
or we find a use for it. Now, I want to maintain it and make sure that it doesn't fall into disrepair. And to do that, the best way to do it is to get involved and get research going and tie in and get money to help maintain it. Like, we won't make any profit out of the dish, but we want to keep it so that the motors are well cared for, that it's oiled and greased, and if there's any parts are breaking, they're replaced. It's something that it would be an awful shame for it to fall into disrepair and not be used, to be honest.
So there's no commercial use for this other than...
There is, but you can, nowadays, for most of the commercial uses, you can use 4-meter dishes. The technologies for dishes have moved on a lot. And like I could buy a 4-meter dish for a couple of €100,000. So and you see what happens with the satellite industry is, like, for example, the KSAP one I showed you.
Yeah.
Every new contract, they have 0 failure rates. So everything is bought new. And for the life of that contract, everything is kept for the life of the contract. At the end of the contract, these are binned. They're not used by the commercial industry anymore. And that's why we're involved in the research side, because one of the big opportunities here is as stuff comes to end of life, it suddenly becomes available for research. And rather than have it thrown away or dumped or binned, to have European ESA, FP7 and all these type of research projects going means that it can tie the two together. Even, say, the KA one right now for the moment, that thing is going to be broadcasting internet across Europe. But between 12 o'clock or 1 o'clock at night and 6 o'clock in the morning, there's virtually no traffic because everyone's asleep. Now, at that time, it's possible we can do a deal between the universities and Eutelsat for research stuff to be done in the middle of the night. Way cheaper than it would cost for commercial access to the satellite. And that's the kind of thing, and for Eutelsat it's a win-win because they're using empty space. For the research establishment, they're getting to do research that they couldn't possibly afford to do, and you have access to this €600 million piece of infrastructure that's now been built. So this is why we want to bring the two together. You know? Any more questions? Yep.
Who are behind the National Space Centre?
Well, there's myself, a bunch of Cork investors, Enterprise Ireland are a shareholder, and there's a company a small company in Dublin involved as well.
It's more a question for Dr. Smith perhaps, but I was wondering what frequencies are you going to be detecting? I presume they're extragalactic radio waves.
That'd be for Dr. Smith.
And what physical phenomena are you studying, in those wavelengths?
Okay, yeah. So we're going to start with two wave bands. One is 21 centimeter for neutral hydrogen, and the other is 4 gigahertz.
The water hole, is that what it's?
Yeah,
Yes.
they're both in the water hole. The reason for going to 4 gigahertz is that there's already a very elaborate waveguide system which takes the signal down at 4 gigahertz. So that allows us to put our detectors right on the ground in the control room rather than up higher up. So it's very convenient to feed that down. And as you correctly point out, 4 gigahertz is in the water hole. The standard observational frequency in astrophysics, there's a number of them. One of them is 5 gigahertz. So we're going to be slightly away from that. But what people normally do is they stick their hand together and say, right, let's all look at 5 gigahertz together. And then at least everybody compares the same frequency. 4 gigahertz is sufficiently close so that we'll be able to either give complementary data or data that's very similar, because if you're emitting that much at 5 gigahertz, for the most part in radio, what you're doing at a couple of gigahertz either side of that is similar for the most part. Now there are exceptions, but so the 4 gigahertz is really because of the system here, the 21 because of the waveguide structure that's already in the system, and the 21 centimeter is because neutral hydrogen is everywhere. So there'll always be a signal for us to see. You don't do a lot of research on 21 centimeter, you do a lot more research on the 4 gigahertz. So what might we do? Well, I should say that primarily in the first stage, this isn't going to be a research grade instrument, because the detectors that we will, if it's scanning only, it's very hard to calibrate those detectors. It's not impossible, but it's very hard to do so. So in the first instance, it will be, we'll all be getting to learn the system a little bit. It's really when we can move it and point it that you get that higher grade research. But one thing that we're very interested here is in quasars. And what we do here is we look at them in the optical, and we look at them varying in the optical. But one thing that's really neat that you can do is compare the variations in the optical with, say, variations in the radio. So when we were able to do this, the science that you can do by having 2 wave bands is hugely more than the science you can do with just one. So that would be one thing that we could do. But there's then other things like pulsars, for example. And what people do is, pulsars are these stars that spin, and they basically spin at different rates depending on how old the pulsar has been. But some of them will rotate 33 times or 100 times a second. Some will be every few seconds. And these stars are actually about 10 miles across. So, but the beams of radiation they send out, they go click, 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 click. But every so often they go click, click. And we don't know why. Well, I don't know why. They're not an area of expertise now of us. But by looking at those with a telescope like this, we can provide additional data, which then others can interpret. And ultimately what we will be looking for is to do what they do with a lot of these types of facilities, which is spend some of the time being used by professionals elsewhere in the world to take data. That will only happen if we get these Rolls-Royce detectors, though, I have to say. They won't do it otherwise, for the most part. So we're a little way away from that. So then there's other things like, for example, every now and again you have supernovae, like these exploding stars. If you could get some extra data, that would just add into all the other data that's been taken around the world. That would be helpful. And then there's other things which are and again Rory mentioned it, the sun emits flares. You can monitor the sun. Now, you don't actually need a 32 meter to do that. In fact, the danger is you don't want to be pointing a 32 meter directly at the sun and the detector is all getting fried on the far end. But then Jupiter is another one you can do. There are lots. For us, it's the quasars. That's where our interest is. And it's measuring the quasars in the optical and in the radio simultaneously. And by simultaneously, just as a final comment, I know I've answered your question very long-winded. You can use telescopes in places like Spain or the Canary Islands or in Greece, because they share the same part of the sky with us for a large part of the night. So we could be seen from Middleton the object. It might be cloudy, so we can't see it with our optical telescopes, but it might be clear in Spain, and they'd be able to see it with their optical telescopes. So by forming networks, you can do really neat things.
So